So moving on with Faraday's law, which we kind of started a little bit in the last video, um, we saw in the examples that we were working with that if we slide a bar along conductive rails, then that's a source of induced EMF if it's in some kind of magnetic field. We also saw that it is a way that we can change the magnetic flux. So as we move the bar, we're changing the amount of area in the shape that's bounded by the bar and the rails. So depending on how we slide it, we could make kind of that rectangular area either bigger or smaller. So the scientist Michael Faraday, he actually discovered that the two things don't really exist independently. The induced EMF that we get when we move that bar is actually a measure of how the flux is changing over time. In calculus, this is going to be a derivative, but since we're just algebra based, we don't have to worry about it in those contexts. The induced EMF is going to be equal to, we said change in flux, too many Greek letters, change in flux over a change in time. So this formula, this is Faraday's law. An induced EMF is just a rate and change in flux over time. So we had an example earlier of a bar rolling along tracks to induce a current, and that's just one case of Faraday's law. If the bar moves at a constant velocity, so it's covering some distance delta x over some time delta t, then we can say that the EMF is equal to VBL. Nothing new here, we've had this before. VL. And if we're saying delta x and delta t, it covers this distance in this amount of time, then we can replace V like this. So delta x over delta t, that's like the very first equation that you learn in physics. V equals delta x over delta t. VBL to finish that off. Alright, we can rearrange this a little bit. We're going to set ourselves up to make some substitutions. So I'm going to put everything in the numerator together. So delta x BL. So B is magnetic field and L is length of the bar. I'll put all that together in the numerator and then divided by delta t. I really need to get myself a pen so I can just write this stuff and not have to fight with copy and paste and all these Greek letters. Alright, so we scroll down a little bit here. We can see in the numerator we have delta x times L, or delta XL. That's the same thing as an area. If you multiply one distance by another distance, you get kind of the square, so it's an area. So if we make that substitution, then we'll see that EMF is equal to, we're replacing delta XL with A, so B times A divided by delta T. But we know what BA is equal to. We set up an equation for that as well. So if we make that substitution, we know that B times A, that's the flux, the magnetic flux. So magnetic flux divided by delta T. EMF is flux over T, or change in flux over T, which is the equation that we said earlier is Faraday's law. We just kind of set that up and showed why they're the same thing. Alright, so that's Faraday's law, and on to Lenz's law. So Faraday's law tells us that a change in magnetic flux, delta phi, induces a current in a loop of conducting material. But what it doesn't tell us is what direction that current is going to flow. So that's where Lenz comes along, and he says that the current is going to flow, current flows, so that it's going to opposes the change in the magnetic field. Change in magnetic flux by creating its own magnetic field. So I was telling a few people earlier today that things in nature, everything in nature is inherently lazy. Nothing wants to change. Everything wants to just keep doing what it was doing. Leave me alone. I don't want to do any more work than I have to. Which a lot of you know how that is, don't you? But I mean that's the way that everything works. So Lenz's law just says that we have these charges sitting in this loop of conducting material, and they don't want to be bothered. So if we introduce them to some kind of magnetic flux, there's some kind of magnetic field going through that loop, they're going to do everything in their power to make it so they don't have to leave their spot. So they're going to adjust themselves so that they kind of cancel out that magnetic field that was introduced. Otherwise, they'd just be running around forever. So they kind of shift a little bit to get rid of that annoyance, the magnetic field that was added. So we have a right-hand rule that we linked to current and magnetic field. It was the one where your thumb was the current, and if you were going to grab a wire, your fingers would curl around. We're actually going to use that one again, but we're going to change it up a little bit. So with this right-hand rule, now we're going to use our thumb to represent magnetic flux. So if you have a loop of wire with a magnetic field coming out through the center, then our thumb would point into the center because we want to create this magnetic field that would cancel out the one that exists already. So if it's coming out, our thumb would point in, and then we kind of curl our fingers around to show which way the current would move around this loop of wire. So if we had a magnetic field coming out of the loop would try to change it so it goes into the loop. So your thumb would point in, fingers curl around in a clockwise direction. So your fingers here are going to tell you which way current flows in a loop, whereas before current was your thumb, magnetic field was your fingers. So just a little change there, but still same shape to link current and magnetic field. So we can actually just make one tiny little change to Faraday's law to get Lenz's law. So let's grab Faraday's law. Okay, apparently I can't do that, so we'll go ahead and do this. There we go. Alright, I'm going to get rid of this stuff in the middle. So this was Faraday's law, and induced EMF is equal to change in flux over time. So the little change that we're going to make is right there. We're just going to throw in this minus sign. So Lenz's law looks almost identical, except it's negative. So Lenz's law will take direction into consideration when you're using it there. So example. So we had a square in the previous example. It had sides of length 2 meters. It was in a magnetic field of strength 10 teslas. and it's rotated by 60 degrees in the course of 4 seconds. We want to know what is the induced EMF in the square and in what direction is the current going to flow. Alright, so in the last example we said that the change in flux, we found the change in flux for this rotation to be negative 20 Webers. So that chunk of the work is already done. All we have to do now is figure out what is the induced EMF, which we can use Lenz's law for. So EMF is negative, change in flux over time. So we take negative, our change in flux was negative 20 Webers. And the change in time we're given in the problem is 4 seconds. So negative 20 divided by 4, that's 5 Webers per second, which is the same thing as saying, since it's an EMF, 5 volts. So 1 Weber per second is the same as 1 volt. So as for determining the direction of the current, first we need to figure out what's the direction of the change in flux. So from the diagram that we saw in the previous example, let me scroll back up to that. So from this diagram, we can see that the magnetic field lines are moving in the upward direction. So since we're rotating the square, it's not perpendicular anymore, and we're decreasing the flux. So that's kind of like saying we changed our magnetic field from going up so much. We actually changed it downward. That's what the negative is telling us. So since the magnetic flux changed by negative 20, that's kind of the same thing as saying that it changed by 20 Webers in the downward direction. So it moved down 20 from what it was. So the direction of the current now has to be such that it's going to oppose that downward change in flux. So yes, the magnetic field lines are still going up, but it's kind of like our flux, the amount that is getting through our loop has gone down. So the down part, that's what we want to go against. So our current has to produce a magnetic field upward to try to undo that change. So point your thumb of your right hand upward and then wrap your fingers around it in a fist, and you'll see that for this loop they go in a counterclockwise direction. So that's the direction that the current has to flow, has to go counterclockwise. So current has to flow counterclockwise to, we'll say, counteract the downward change in flux. So negative 20 would be downward 20. So Lenz's law is really just a special case of conservation of energy. So we're going to look at that example of the bar sliding on the rails again. So what happens if the induced current doesn't oppose the change in flux? So we said then that our current is flowing counterclockwise. The current in the bar is flowing toward the top of the page. So the magnetic field exerts a leftward force on the bar. And that's the way it has to be to make sense. There has to be, if we look at what would happen if current flowed the other direction, then the force on the bar is actually going to be to the right. So we'll have some external force moving to the right. The bar would also experience a magnetic force to the right. So everything would be accelerating, getting faster and faster and faster. We would be getting all this extra speed and kinetic energy at no cost, just coming out of nowhere, and energy would not be conserved in that case, which you should know from last year is like red flag that everything you're doing is wrong if energy is not conserved. So that was how we can change the flux by changing area. We can also change the flux by changing the magnetic field. So so far we've done increasing the size of our conductive loop and by rotating it in a magnetic field. Third way is if we keep the circuit or our loop still and just change the field around it. So if you have a permanent magnet that moves toward a loop of wire, the magnetic field at the loop changes. You can kind of see in this picture here, when the magnet is farther away, only these two little lines are making it through. But if we move the magnet a little bit closer, we have a whole lot more lines in there. We can see that the downward flux, since it's coming out of the negative end, the downward flux is increasing. So important to remember that your field lines come out of the north and go into south. So as the magnet gets closer to the loop, downward flux increases. By Lenz's law, the current that we need has to be in, it has to create a magnetic field in the upward direction. Since our flux is getting more downward, more negative, we have to get an upward to balance it out. So if we use the right-hand rule, we can see that current would flow counterclockwise as those arrows in the loop indicate there. So once the middle of the magnet passes through the loop, the flux starts to decrease in the downward direction. So if we're decreasing the downward flux, that's the same thing as saying that we're making a change upward. The double negatives kind of cancel out into this positive upward direction. So once the magnet is halfway through, right at the middle point, then the change in flux moves to upward. And the current has to change direction and flow clockwise. So to counteract the upward change, the loop would say, all right, now we need to create something that's going downward, and it would start flowing the other direction. So you can see that in these pictures here. Once it's made it through, then it starts to change upward. The downward flux decreases. So it really doesn't matter whether it's the magnet that's moving or the loop that's moving. They just have to be moving relative to each other. One of your things has to be moving, or they could both be moving.